Hi, everybody. It's Professor Mitchell. Today we're going to start Chapter 2 on Introduction to Logic and Sets. And in this section, we're going to talk about reasoning and logic and introduction. So the objectives of this section are to talk about quantifiers and their effects on statements, different forms of statements, how to determine whether two statements are logically equivalent, how to develop logical arguments, how to determine whether an argument is valid, and that's it. So let's start with a few definitions. First of all, when we talk about statements, we're talking about a sentence that is either true or false, but not both. And then the negation of a statement is a statement that has the opposite truth value of the given statement. The negation of a true statement is a false statement. And the notation that we use for negation is this little tilde squiggle thing. So notice I'm using P to stand for the statement. The most common letters that we use for statements are P, Q, and R, but you can use other letters. So if the statement P is true, then the statement negation P is false, and also vice versa. If P is false, then the negation of P would be true. All right, so let's form the negation of each of the following statements. The first one says 2 plus 3 equals 5. Remember, the negation has to say the exact opposite thing. So that would just be 2 plus 3 does not equal 5. It's pretty simple, right? The next one is a hexagon has 6 sides. The negation would be a hexagon does not have 6 sides. Notice that both of the original statements happen to be true, and so the negations are false. All right, a few more definitions. When we talk about a quantifier, we're talking about words such as all, some, every, there exists, and no or none. So these are words that describe how many things the statement applies to, all right? And we're not getting really specific like 2 or 7 or anything like that. It's either all of them, none of them, or some of them. There exists really means the same thing as some. In logic, some means at least one, all right? So it's a little different than everyday English. A universal quantifier applies to every element in the set. So those would be things like all, every, and no. So when you use a sentence that starts with one of those words, you're saying that the statement that you're making applies to every single one of those things, whatever you're talking about. All right, and then if you want a quantifier that only applies to some of the things, you're using an existential quantifier. That applies to one or more, or possibly every element in a set. So, for example, the word some could mean all right? It's not very specific. Again, some means at least one, okay? So the words some and there exists are existential quantifiers. Okay, so one thing that students find a little confusing at first, it turns out to be pretty simple in the end once you've thought about it for a little bit, is how to negate a quantified statement. So for example, if you take the statement, all students like hamburgers. Now remember, your original statement and the negation have to have opposite truth values, okay? So let's just use common sense here for a minute. All students like hamburgers, that's probably not true, right? I mean, some students are vegetarians, okay? So the first inclination of a lot of people is to think that the opposite of all is none. No students like hamburgers. But that can't be right because that's not true either, right? So it turns out that the way you negate a statement involving all is to say some are not or some do not. Some students do not like hamburgers. That's exactly the reason that the statement all students like hamburgers is false, because there are some students who don't, right? Students who are vegetarians, for example. All right, some people like mathematics. That's true, right? Hello. And so again, the first inclination of a lot of people when they're trying to negate a statement that says some is to say some are not or some do not. So if you think about the statement, some people do not like mathematics, well, unfortunately, that's also true. Okay, so that cannot be the negation of some people like mathematics. If you disagree with the statement, some people like mathematics, that means you believe that nobody likes it, okay? So think about that, all right? Okay, continuing, we're negating each of the following. Notice it says regardless of its truth value, okay? So this one says there exists a natural number n such that 3n equals 6, okay? So we're getting very mathematical here. So, you know, think about one of the problem-solving strategies that we talked about back in chapter 1, you know, relate it to a problem that you've already done. And remember that there exists means the same thing as some. Some natural numbers have this property, okay? And so from letter B, we know that the opposite of some is none, okay? So if you don't agree that there exists a natural number n such that 3n equals 6, you're saying no natural numbers do that, okay? And another way of saying that is for all natural numbers n, 3n does not equal 6, okay? So let me try to help you understand this a little bit better. There exists is an existential quantifier, okay? So when you negate a statement with an existential quantifier, the negation is going to start with a universal, all right? So that's why the negation starts with for all, and then you turn the statement being quantified, 3n equals 6, into its opposite. 3n does not equal 6, all right? So there exists an n such that 3n equals 6. The opposite of that is for all n, 3n does not equal 6. So change the existential to universal and change the statement to its opposite, all right? Please, 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 at any time, you know, if you need to stop and think about something for a minute, just pause the video. That's one good thing about doing this from video that you can't do in class. All right, here is a universal statement for all natural numbers n, 3n equals 3n. All right, so, you know, trying to apply what we did in letter C, we changed the existential to universal, and then we changed the statement to its opposite. So let's try that with this one too. This one starts with a universal. So we'll change it to an existential, and we'll change the statement 3n equals 3n to its opposite. So that would say there exists a natural number n such that 3n does not equal 3n, okay? So just to recap, in letter C, this is really the same thing as some are, and the negation is none are. And in letter D, the original statement is all are, and the negation is some are not, all right? So, I mean, those are really the only two things you have to remember. All are and some are not are opposites. Some are and none are opposites. So if you can just hold on to that, that should help you with these quantified statements. All right, so now we get into truth tables. A truth table is a symbolic system to show all possible true-false patterns for statements. And so what you're looking at here is one of the simplest examples. Let me explain this to you. So over here, it's saying that a given statement P can be either true or false. And what this is saying over here is that if the original statement is true, then the negation is false. And if the original statement is false, then the negation is true. That makes perfect sense, right? Okay, after that, it gets a little more complicated. So the next logical operation that we should talk about is called conjunction. A compound statement created from two given statements using the connective and. So conjunction means and. And we use this upside down V symbol to represent and. And a conjunction is true, excuse me, only if both statements are true. Otherwise, it's false, okay? And I think that kind of makes sense. Just, it works the same way in everyday English, okay? So there are four possibilities for the true-false combinations of your two statements. Either they're both true, or first one's true, second one's false, or first one's false, second one's true, or they're both false, okay? And over here, it's showing that the conjunction, the and statement, is only true when both statements are true, okay? So think about the statement, you must be 18 years old and a US citizen to do something. I don't know what, all right? So think of the statement, you are at least 18 years old and you are a US citizen. That statement, including the word and, would only be true if both parts of it are true, okay? All right, then we get into disjunction, a compound statement created from two given statements using the connective or. So disjunction means or. And we use this symbol that does look like a V to represent or. A disjunction is false only if both statements are false, all right? So, you know, just think about everyday English use of the word or, all right? One or the other. The only time that doesn't work is if both parts of it are false, okay? So this example doesn't work as well as it used to. Back in the old days, we used to require students to either pass a placement test to get into Math 20A, or they had to pass a class called Math C, which was intermediate algebra. If you passed intermediate algebra or you got a good enough score on the placement test, you can take Math 20A, okay? So the only students who would not be allowed to take Math 20A are the ones who didn't pass Math C and also didn't get a high enough score on the placement test, all right? As long as you did at least one of those things or even both of those things, so that's where the word or is a little different from everyday English. In logic and in math, or usually means and or, one or the other or both, all right? So I can't imagine a student would take Math C even though they also got high enough score on the placement test where they didn't have to. I think some students have done it, but that student would definitely be allowed to take Math 20A. All right, so let's look at this example. They want us to classify each of the following as true or false. These statements down here, really, all right? But first, we're going to have to decide whether the statements P, Q, and R are true or false. So pretty easy to decide. P is true, Q is true, however, R is false. So if we look at letter A, P and Q Well, both statements are true, so that means the conjunction is true. That's a pretty easy one. Oh, I'm sorry. I thought I caught all of these. So I noticed when I was going over the PowerPoint that all of the conjunction and disjunction symbols had been replaced by these little question mark boxes, and I thought I got them all. Okay. All right, next, letter B, Q or R. So remember, statement Q is true, statement R is false. However, this is a disjunction. The only time a disjunction is false is when both parts of it are false. So this statement right here, Q or R, that is a true statement. And I missed that one also. I really did think I caught all of these. Okay. Good thing I'm not going for perfect in these videos. All right. Oh dear, I hope I caught the next one. Let's see. Not P or R. Okay, so now it's getting a little more complicated. So P is true. That means that not P is false. I think it might be helpful to scribble a little something underneath the two parts of this. So the statement not P is false, and we already know the statement R is false. And if I put a disjunction between those, that is a false statement. So let's see how that looks. Nope, didn't catch that one either. Goodness gracious, what was I doing? Okay, now what happened to my, here we go. All right. There we go, that is a disjunction. All right. So let's see what we have next. Okay, this one I'm pretty sure I did fix. All right. Continuing the same example, we have P is true, Q is true, R is false. So now they want to know if the statement not P and not Q is true or false. Well, remember P and Q are both true. So that means that not P and not Q are both false. And if I put a conjunction between those, that is going to be a false statement. Yes, I did catch that one. All right. Oh, now this is interesting. They've put parentheses around P and Q. All right, so let's see. Didn't we do P and Q on the previous slide? Yes, we did. We decided that the statement P and Q was true. All right, so no need to reinvent the wheel here. We'll just say that this whole thing here is true. However, when I put a negation outside it, that makes the whole statement false. All right, and that brings us to letter F. P and Q, which again we already know is true, or not R. And remember, R is false. That means not R is true. And if I put a disjunction between those, that is going to be a true statement. All right, let's see what's next. Aha, this is one of my favorite things. Conditional and biconditional. So let's start with conditional. A conditional or implication is a statement expressed in the form if P then Q. Notice the notation we use for that. We use this arrow pointing in one direction. Later we're going to have an arrow pointing in two directions. The if part of the conditional is called the hypothesis. So that would be the statement P. And then the conclusion is the then part of the conditional, which is Q in the statement if P then Q. So here's an example I cooked up a long time ago. Suppose, pretend, all right, as in not real, that I made this promise. If you get a tattoo of the quadratic formula, I will give you an A in the course. All right, so notice my disclaimer here. I am not giving out A's to people who go out and get a tattoo of the quadratic formula. I would probably admire it and maybe want a picture of it, depending on where it was. But I'm not giving you an A for that. All right. So under what circumstances would I break my promise? Okay. Well, let's look. So here's the statement again. If you get a tattoo of the quadratic formula, I will give you an A in the course. Under what circumstances would this promise be broken? Oh, and hey, look at this. Somebody's actually gone out and done that. I actually found a few of these on Google Images that clearly belong to different people. So there are some people who will go out and do this. I don't know if it was to get an A in their math class. Probably not. All right. So one scenario is you get the tattoo and I give you an A. I have not broken my promise. So that would be the statement, if you get a tattoo of the quadratic formula, I will give you an A in the course. That would be true. Okay. Now, suppose that you got the tattoo and I didn't give you an A. Then I think I've broken my promise. And that would be a false statement, that if-then statement. Now, here's where it gets a little weird. Suppose you don't get the tattoo, but I give you an A anyway. I bet a lot of you are hoping that that's the scenario that's going to happen. All right. Well, in that case, I have not broken my promise because there's no promise to break, right? I mean, my promise was dependent on you getting the tattoo. So if you don't get the tattoo, all bets are off. And in that case, I have not broken my promise. And that would have to be considered a true statement, the if-then statement. Okay, you might want to sit with that one for a minute because I admit that's a little weird. And then finally, you don't get the tattoo and I don't give you an A. Again, all bets are off. I have not broken my promise. So there's really only one scenario where I've broken my promise, and that's where the first part of the if-then, the hypothesis, is true. But the second part, the conditional, is false, all right? So that leads us to the truth table for conditional. So notice that the only place there is a false in the answer column is right there. So only in the case where the first part is true and the second part is false. In all other cases, the statement if P then Q is true. Okay. All right, let's see what else we have. Okay. Any implication if P then Q has three related implication statements. Notice the word related. So I don't want you to think that these three statements necessarily have the same meaning as the original. Okay. So the first one of those is called the converse. This is a word we use in math frequently. The converse of the statement if P then Q is if Q then P. Okay, so it's just turning the statement around. If you get an A in the course, that means you got a tattoo of the quadratic formula. Well, hopefully that's not how it works. All right. The next one that's related is called the inverse. If not P, then not Q. If you don't get a tattoo of the quadratic formula, then I will not give you an A in the course. Again, hopefully not true. All right. But then there's the contrapositive, which says if not Q, then not P. If you didn't get an A in the course, that means that you did not get a tattoo of the quadratic formula. Think about, does that have the same meaning as the original statement that I made earlier? If you get the tattoo, then I will give you an A. Okay. We will answer that question in a little bit, by the way. All right. This is a great example, especially for those of us who live in California, because this will really give us a feeling for which of these statements, the converse, the inverse, and the contrapositive, have the same, well, at least the same truth value as the original statement. So the original statement is, if I am in San Francisco, which from my background, it looks like I am, spoiler alert, I'm not, then I am in California. Okay. Well, that's a true statement, isn't it? If somebody is in San Francisco, then they have to be in California, right? Because all of San Francisco is inside of California. The converse, remember, that's just where you switch them around. If I am in California, then I am in San Francisco. Well, that doesn't work, does it? Because I bet that most of you watching this right now are in California, but you're not in San Francisco. Okay. So I don't think that means the same thing as the original statement. And in fact, the original statement is true, but this statement is could be false if you're watching anywhere in California besides San Francisco. The inverse says, if I am not in San Francisco, check, then I am not in California. Oh, but I am in California. So again, I would imagine that this statement also applies to 99% of you who are watching. You're not in San Francisco, okay, but you are in California, right? Probably almost all of you. So that statement doesn't necessarily work. However, if I am not in California, all right, a few weeks ago, for example, I went to New Jersey to visit my family. If I am not in California, then I am not in San Francisco. Check. I was in New Jersey. I was not in San Francisco. So it turns out we're going to actually prove this in a minute. The contrapositive has the exact same logical meaning as the original statement. Okay, but the converse and the inverse do not. All right, those are different statements from the original. Okay, so now what we're going to do is we're going to use a truth table to prove, and I have a new symbol to explain to you, that the statement if P then Q is equivalent, that's what this 3-bar equal sign means, is equivalent to the statement if not Q, then not P, which remember is the contrapositive. Okay. All right, so here is the truth table all filled out, but I'm going to walk you through this one step at a time. I about drove myself crazy setting up some animations for this. So the first thing I want to point out to you is in any truth table involving two statements, it's a good idea to fill it out under P, write true, true, false, false, and under Q, write true, false, true, false. If you do it that way every single time, you will hit every possible combination of, P being true or false, Q being true or false. Okay. So the next thing I want to point out to you is the column under if P then Q. This is what we went over a little while ago. The only time it's false is when P is true and Q is false, right? The next thing is the negation Q. So notice under negation Q, I have exactly the opposite of everything that is under Q. Instead of writing true, false, I wrote false, true. And then I did the same thing to P. Instead of writing true, false, I wrote false, true. All right, so now I'm ready to fill out the column under if not Q, then not P. All right, so I am actually going to add a little drawing to this. Okay, if I circle these two columns, notice that there is only one row where the first part is true and the second part is false, and that is exactly the row where I have a false over here. Okay, because remember, conditional is only false when the first part is true and the second part's false. Okay. So now what I want to point out to you is that this column is exactly the same as this column over here. And that's what it means for the two statements to be logically equivalent. No matter whether you plug in true or false for P or true or false for Q, The columns under the equivalent statements are exactly the same. All right. Let's see what we have next. If you catch me pausing sometimes after I've just been drawing on the PowerPoint, it's because for some reason I lose track of my mouse. It disappears after I've been drawing, and sometimes it takes me a little bit to find it. So, okay. That brings us to the biconditional. The conjunction of a statement and its converse is called the biconditional. It is written like this with the double arrow and is read P if and only if Q. We use if and only if a lot in math, and sometimes I hear it used in everyday English. It means that the first thing will happen only if the second thing happens, and the second thing will happen only if the first thing happens. So notice what we have here. We have our usual true, false, true, true under if P then Q. Under if Q then P, it's a little different because notice, let's see. Well, the first part of if Q then P is Q, right? So that would be the true and then false in the opposite order of how they usually look. So the first part of this statement is Q, and in this row Q is true, P is false. So that would make this statement false. Okay. So now remember how conjunction works. Conjunction is only true when both statements are true, and that happens a couple of times, right? It happens here, and it also happens here. So the moral of the story is that your biconditional is true if P and Q are both true, or if they're both false. All right. So, just think about what I said a minute ago. If and only if means the first thing happens whenever the second thing happens. If the first thing doesn't happen, then the second thing's not going to happen. All right. So that's what biconditional means. And I've lost my mouse again. Oh, you know what? Here's a little trick to find it. I just scribble and then there we go. Okay. All right, little bit of valid reasoning. Reasoning is considered valid if the conclusion follows unavoidably from true hypotheses. So for example, if your hypotheses were all cats like fish and Felix is a cat, well then that must mean that Felix likes fish, right? Doesn't that make sense? So one tool that we use to determine whether arguments like this are valid or not is to use something called an Euler diagram. Notice how I pronounce this word. It looks like Euler, but it's pronounced Euler. It's German. Euler was one of the greatest mathematicians of, I believe, the 1800s. And so these diagrams are named after him. So the first hypothesis was all cats like fish. So the circle representing cats goes inside the circle representing things that like fish. So other things that would be inside this big circle would be some people, seals, walruses, okay, anything that eats fish would be inside this big circle, and in particular cats would be here. Felix is a cat, so we can represent Felix with a dot inside the cat circle, and that forces Felix to be inside the big circle of things that like fish. Okay, absolutely no way to avoid putting Felix inside the likes fish circle. Okay, so that's called an Euler diagram. All right, here's another example. I believe this is the last one. Determine if this argument is valid. So the hypotheses are, in Washington, D.C., all lobbyists have influence. And the second hypothesis is, no one in Washington, D.C. over 6 feet tall has influence. And they're saying that from those two hypotheses, you can conclude that people over 6 feet tall are not lobbyists in Washington, D.C. Okay. All right, so let's look at the diagram for this. All right, so L represents lobbyists. I represents people who have influence. Okay. So the statement, all lobbyists, first of all, this whole thing is happening inside of Washington, D.C. So I think we can kind of ignore the Washington, D.C. part. So the first part is all lobbyists have influence. So the lobbyist circle goes inside the people who have influence circle. And then the second statement said, no one in Washington, D.C. over 6 feet tall has influence. So let's make that a little simpler and just say nobody over 6 feet tall has influence. All right, I hope that's not true. I happen to be 6'3". Okay, so they're using W, and I kind of wish they hadn't done that, and I would have liked to have changed it, but there was no easy way to do that. They're using W to stand for people over 6 feet tall. So when you say nobody over 6 feet tall has influence, you just draw the over 6 feet tall circle completely separate from the has influence circle. And then by doing that, unavoidably, the people over 6 feet tall circle is completely separate from the lobbyist circle. So that means that nobody over 6 feet tall is a lobbyist, and that's the conclusion that they wanted me to decide if it's valid. All right, so again, L represents lobbyists, I represents people who have influence, and if W represents people over 6 feet tall, the second hypothesis is pictured over here, and the conclusion is valid. And that's going to do it for logic. So next time we will start talking about sets.